Yeah, so good morning, everybody. Thank you for coming again so early after the yesterday's program. Yeah, based on your feedback from yesterday, we have asked for air condition. So today, hopefully, the climate here is going to be better. So thank you for the feedback. And if you will need something more, just tell me and we will try to do our best to provide you the best comfort. So let's briefly tell something about today's program. We will start with a presentation of Francesco in a few minutes, which will be followed by coffee break and Jan's presentation. Then afternoon, after lunch, which is again here, we will have practical seminars. So the organization is going to be like it's provided here, which means that you will be split into two parts. One part, the groups A, B, C, and I, which is on your badges. So follow the letters that you have there, not how you have been distributed yesterday. So it's really the how it's written there, because the capacity of rooms is limited. But you will have, all of you will have the same practical exercise. So this group will, so ABC, I will stay here for the second part of Francesco's seminar presentation, and then D and E will go to room E132, and groups F, G, H to E230. Then after the presentation will finish, the people from here, from the presentation room, will continue to a lab tour where we are going to visit few labs in our departments here in this campus, and the rest of the people will still continue in the practicals. So the practicals will take from 1:15 to 3:30. So you have a lot of time to learn something. Then there will be coffee break, short presentations of students as yesterday, and the groups will be swapped. So group A will go to the E132, group B, C to E2030, and the rest of the people will have the same presentation from Francesco, which will be provided twice. So thank you, Francesco, for such a big effort and 3 presentations today. And yeah, we will for sure enjoy it. So if you have no questions regarding today's program, do you have question? If not, if you have still, you can ask me or anybody during coffee break. So I can ask Francesco to tell us something about coordinated fast planning for information gathering in multi-robot systems. Thank you for coming.
Thank you. Okay. So can you hear me? Should I speak louder? No. Yeah. Okay. Okay. So good morning. My name is Francesco Amigoni, and as usually is a good thing before starting a presentation, is a good idea to introduce myself. So I am from Politecnico di Milano, Italy, and I am part of this lab that is called Artificial Intelligence and Robotics Laboratory. And in Italy, we have this system in which we don't have one professor, one lab, but we have one lab, several professors that are in the same lab. In particular, in my lab, we are 9 professors. I am associate professor from 2007, and I usually teach courses at the master level and at the PhD level that are artificial intelligence, autonomous agents and multi-agent systems, and intelligent multi-agent systems. And from the name of these courses, you can guess that my field or my background is not in control, but is in AI. So I'm usually doing research in between AI and robotics. So just I usually publish papers at ICRA, IROS, but also at AMAS and at AAAI, so that are more AI-oriented, oriented conferences. So in the past, my research was more on architectures for multi-agent systems, but currently I'm doing research in, let's say, generally speaking, in the autonomous decision-making for physical systems, so for systems that are working in the physical environment. So the main application of this kind of techniques is in robotics, of course, but we have done works also when these agents that are acting in the physical environment are appliances in your house, or are satellites in the space, or are electrical devices like switches, or are also control systems for dams. Okay. So the main idea is that we are working on making good decisions, or making algorithms for making good decisions in problems in which you have several decision makers, so multi-agent systems, that are acting at the same time. And as I said, the main field of application is robotics. Okay, so what I'm going to present in this lecture. So first of all, I will show some motivating examples for information gathering for multi-robot systems. Then I will, step by step, try to identify 3 canonical tasks, as I have called them, that are 3 typical tasks for information gathering that are the coverage, exploration, and patrolling, and I will explaining what they are different and what are the features that characterize each one of these tasks. And then, of course, I will make some conclusions. In the 3 main canonical tasks, I will show you the general problem, so how the general problem has been defined or can be defined, and several variants of this problem, and then I will show you a sample of some solving approaches that have been proposed for solving these specific problem. So I have to make at this point a number of disclaimers. So my goal is not to cover the state of the art. So I will just sample some idea. I will just present you some ideas. I cannot present all the ideas that have been proposed in this field. And how I have made my selection of idea that I will present to you, it is made by my personal knowledge and experience, and I know that it is a little bit AI-based, but I would like to present you things that I know better, of course. This does not imply that these techniques that I will present to you are the only one that can be used for the problems, okay? It's just a sample. The level of details of my discussion will be at the level of general ideas behind the algorithms. I will skip several details, actually most of the details, because going in depth with each one of the techniques will require, let's say, 1 hour for each technique. And as far as I could, I tried to be independent of specific robot platforms and sensors mounted on robots. So I tried to be as much as possible at the algorithmic level, with the idea that then you can take these kind of algorithms and then customize them for your specific system or for your specific application. Okay, so it's time to start with the introduction. So I will just show you 4 multi-robot system applications that you, of course, know, okay? We can have multi-robot systems that are employed in search and rescue missions, in a disaster site, or we can have multi-robot systems employed in monitoring applications, or in space exploration, or in patrolling and environment. So these are 4 examples of the several applications that can be taught or that can be deployed for any multi-robot systems. So what is the common ground or the common trait that is characterizing these 4 applications? Is that in all these 4 cases, the robots are going around in an environment in order to collect some data. Okay? The nature of the data is different in different applications. But we can, if we abstract from the details, the technological details of the single application, we can find out these 4 basic ingredients in these applications. So we have multiple mobile robots, so the robots can move in the environment. Then, of course, we have an environment in which the robots move. Then we have some measurements that are taken by the robots. So the robots are able to take some measures from the environment. And 4th element, we have some way to integrate this measurement in a representation that I've called a model. So let's see how these 4 ingredients map on the 4 applications that we have seen before. So if you take, for example, search and rescue, then of course your multiple mobile robots are tractor robots that are moving on the ground, or UAVs, or other kind of also snake robots and other kind of robots that you can imagine. The environment in this case is the disaster site, okay? And the measurements that are taken by the robots are, for example, the presence of victims, the presence of some obstacles, the location of these victims, of obstacles, and so on. And these measurements are usually integrated in a model which can be simply taught as a map with the victim location, with the dangerous objects, and so on. So the same 4 elements can be found also in a monitoring application. So in this case, the robots are robots that are able to move on the water, the surface. The environment is a lake or a river, like in this case. Then the measurements that the robots are making are for example, measuring the concentration of some chemical, and they are able to find their own locations and so on. And the model that integrates all these measurements is the map of the concentration of these chemicals. So you can do like an exercise. You can find out also these 4 elements for space exploration and also for the patrolling. This is the big picture of the context in which we will move in this lecture. But we will specifically focus on some basic questions that I can summarize like this. So our focus will be in decision making of the robots. So when robots are employed in applications like those I have just illustrated, where should they go? And which robot should go there? So this is two of the questions that we will try to answer in this class. Just to make some structure of the several works that have been proposed in this field, I suggest to use the following dimensions. So we can use two main dimensions to classify, to define actually, what are called the canonical tasks. So one dimension is the knowledge of the environment. So do the robots know where they can take the measure from the beginning or not? So at the start of the mission, do the robots know where they can go? Of course, they don't know the measurements that they will take, okay? But at least they know where to go. So this is something that they can know or not. So we will say that the environment is initially known or unknown. And the second element is that is the environment characterized by the presence of other agents? So, or only our multi-robot system is present in the environment? And if there are other agents, are these agents adversaries? Are them neutral? Or are them of any other nature? So this is very important. When I say other agents, this means that they are agents that we have not designed. So we are designing a system, okay, a multi-robot system, and then there are some other agents that we have not designed, that are independent for us. And an adversary agent means that it acts against me. So if I do something, it acts against me. It tries to go against me. If the other agents are neutral, this means that they are just doing what they want, okay, and independently of my presence. So if you combine these two dimensions, you can have, for example, if you consider a case in which the environment is initially unknown, so this means that you initially don't know where you can move to take measurements, and there is no presence of other agents, then we will speak about the problem of exploration. And as another example, if the environment is known and you have the presence of adversaries, so of other agents, we will typically speak about patrolling or target tracking. It depends on the kind of the problem. So according to these two dimensions, knowledge of the environment and presence of other agents, you can find several problems that we will discuss in the following. Then there are some other dimensions that are not affecting the nature of the problem that you are solving, but they are affecting the techniques that you can use for solving this problem. So, and one typical dimension is the possibility of communicating between robots. So it is always possible that robots communicate with each other. So they have a full communication between each other or not. Or it is only possible that some robots will communicate just with the neighbors, or just within some range, or just in some specific in line of sight, or in some other specific situation. So or you can also add some constraints over what the robot should do. So, for example, you can impose that all the data collected by the robot should be delivered to, let's say, a base station. Okay? So this is a constraint on communication that you can add to your problem, but my claim is that this is not affecting the nature of the problem. This is just affecting the nature of the solving system of the solving algorithm that you are using. So typically, if you assume to have full communication, so if you have an application in which the robots can always communicate with each other, then you can easily rely on centralized algorithms. This is because you can centrally compute a plan, okay, for all the robots, and then you can distribute, because you can communicate with all the robots. This is not necessary, okay? This is not mandatory, but it's just something that you can easily do in the case of full communication. If you have limited communication, then you have to use distributed algorithms, and in this case, it is a mandatory. This is because you cannot have a continuous communication between the central planner and the other robots. Okay, so these are the main dimensions that we will consider, and we will focus on high-level planning. So I mean, for high-level planning, what I mean is that we are going to use different kinds, but in all cases, we are going to use some discretized representation of the environment, and we are going to find plans on this. As I said at the beginning, we will abstract from the specific robot platform, so we will abstract from, let's say, the kinematics of the robot and from some other aspects of the movement of the locomotion and of the movements of the robots. Of course, I'm not claiming that this is not important. In application, this is really important to know which platform you are using. But at the same time, it is important to know which kind of problem you are trying to solve. And I will come back to this point at the end of the lecture. So the idea is that if you have an application and you are able to find out in which class the application that you are addressing, in which class it falls, then you can use all the methods that have been developed for that class of information gathering systems. So we will see basically two different approaches for this high-level planning, path planning. The first approach is an offline approach in which we basically, at the beginning, we built, okay, does it work? And this is, okay, good. Okay, yeah, thank you. And in this case, it is an example of an offline plan. So in this case, three robots, the blue one, the yellow one, and the red one, start from here. And I have to go through all these vertices here, or these nodes here. And we can, at the beginning of the mission, plan all their path. This is an example of offline planning. And on the other side, we have an example of an online planning in which we have robots that are, in this case, exploring an environment. The known part is the green one, okay? And in this case, you cannot make a plan at the beginning of the a dimension. This is trivial. So you have step by step to decide where the robot should go. Because step by step you discover more and more of the environment, and then you can allocate robots to go to some specific points of interest in the environment that you are discovering. So this is actually not only related to robotics. So this is in a sense, a very general property of several algorithms, okay, of several classes of algorithms. So we can have these two families of approaches, offline and online. So if you have an offline approach, like in this case with this example here, this is used when the environment is known and static. And this is not difficult to understand since you plan everything at the beginning. So you must be sure that your plans are still valid when the robots are going in the environment. And offline co-ordinated path planning is usually performed in a centralized fashion, and it is usually optimal, okay, up to some, given the discretization of the environment. And the canonical task that is dealing with offline planning is coverage, okay? And we will see several examples of this. Then the other family is online co-ordinated path planning, which is used when the environment is initially unknown or it is dynamic. So in all the cases in which at the beginning we cannot say exactly, or we don't have enough confidence of what can happen in the future. So you would like to make decisions step by step in an online fashion. In this case, the algorithms are usually distributed, and they are usually suboptimal. So it is hard to be optimal in these cases. And the canonical task for this kind of online coordinated path planning is exploration. So the idea is that with offline planning, you are planning the coordination between the robots at the beginning, and with online planning, you are planning the coordination between the robots while the mission goes on. Okay, step by step. Okay, so this ends the short introduction to the big picture to the context that we will consider, and then let me just start with the first of the three canonical tasks that are coverage, exploration, and patrolling. And the first one is multi-robot coverage. So let me formulate the problem in a general way. So what is multi-robot coverage? So it is a problem in which we have a space that has to be covered, and then we have M robots that are equipped with some covering tools. I will be very generic in this. This covering tool can be anything. We will discuss it in a second. It can be a sensor, it can be, let's say, a range sensor, like a a laser range finder, or it can be a point sensor, like a let's say, a temperature sensor, okay? Or it can be anything. So the problem asks for finding the path, a number of paths for the robot, one path for each robot, such that when the robots follow this path, all the points of the environment fall inside the footprint of a covering tool. So this is the basic formulation of the problem. So you have an environment, you would like to cover it, okay? And then you have to plan the path for your robot in order that if you take a point of the environment, this is covered by at least one robot, by the covering tool of at least one robot. Usually you are looking for some optimal solution. So for the objective functions that you would like to minimize are typically the sum of the distance traveled by the robots or the time spent for covering the environment. The time spent is also called the make span. This is because do you know this name, make span? Okay, no, okay. It is really easy. So if you have 3 robots and one takes 5 seconds to cover its part, the second takes 7 seconds, and the third takes 6 seconds, okay? The total time is 7. So it is the maximum of the times of taken by the single robot, okay? And what you would like to do is to minimize the maximum time. Okay, is to minimize the maximum time. Okay, yeah, and in operating research, this is typically called make span. Okay, when you are minimizing the maximum. Okay. Okay, we are usually consider robots that are moving in a discrete space, in a graph typically, and I will go back to this point in a second. There is also a huge amount of work. Also, Jana has worked on this in the past, in which you take this problem from a computational geometry point of view in a continuous space, okay? And in this case, it is called Watchman root problem, okay? But the problems are very, very, very similar, but they just change the representation of the environment. And this problem is not surprisingly NP-hard, okay? Yeah, because it is a difficult problem. Okay, so let me just start from how we represent the environment. So there are several proposals. I cannot, of course, list all of them here, but if I try to take the simplest approach, we represent the environment with a graph, and in which we have the set of vertices that are the configuration of a single robot, and the set of arcs that are the movement between these configurations. And we usually attach a weight to each arc, which is the traveling cost that a robot incurs if it goes along this arc. When I say a graph, this means that the graph, I am not saying how this graph is built. Okay, so you can have on the top here a situation in which you are taking some points, in this case along the walls of this environment here, and then you say that these are your vertices, and the arcs are the straight lines between points that are in line of sight, so that can see each other. So, and then you have this graph here. But when also you have a grid, and like it is quite common in several robots, this is a graph, okay? This is a graph in which the vertices are the single cells, and the arcs are the four connections with the adjacent cells, or the 8 connections with the adjacent cells, okay? So when I say graph, it is actually a very general kind of representation that can be derived from these two representation of the physical environment. And then we supposed to have, as we have said, M robots, and usually it is supposed that these robots are of the same nature, so they have the same capabilities, they are homogeneous. There are several, as I said, there are several variants in which the robots are heterogeneous, so they can do different things and so on. Okay. Now, in multi-robot coverage, one important thing is the covering action. So, what does it mean that a robot covers something? Okay, and this is really, really tricky in some cases. So in the basic cases, it is like a stupid definition, but there are some other cases in which it is actually more complex. So let me start by introducing a generic covering function. It is a function that I've called C that as a domain VK, which means V is the set of vertices, okay, and K is basically the number of robots that you need to perform a covering action. And we will come back on this point. And then, as the codomain in general, we have this P is the power set, okay, is the power set of V to the power of H. So this means that H is the extent of the dimensions of the environment that are covered by a single covering action. Let me just show you some examples and these will be clear. So this is not information gathering, but it helps for grabbing the main idea. So let's assume that you have a vacuum cleaner or a low morning robot, okay. In this case, what is its covering tool? It covers exactly its shape, okay. So when a covering action is, in the case of a vacuum cleaner, is to suck, okay, and it sucks exactly its area, and the same for low morning, okay. And in this case, the covering function is like this. So given a robot in a vertex, okay, in our representation, then that same vertex is covered. Okay? We can extend this. So if we consider the case of monitoring, so this is also called the perception-based coverage. So this means that we have a robot that is equipped typically with a range sensor, okay? And in this case, or like in this example here, is hard to see, but okay, you can imagine what is represented there. So in this case, you have one robot in one vertex, and what this robot covers is a number of other vertices, okay, that are around the current vertex. So you can think of vertices like cells in a grid representation, okay? I am in a cell and I cover some surrounding cells. So from a mathematical point of view, this means that you start from a cell, from a vertex, and you cover a subset of vertices or a subset of cells. You can do also more complex things, like in this case. So in all these cases, we have covered a portion of the environment. But there are some applications, we will see an example later, in which you have to take joint measurements. So this is a typical case when you have to build, let's say, communication maps. So let's say that you have this environment, and let's say that you have some robots here, and then you would like to know from which pairs of points these robots can communicate. And then you have to sample pairs of points, okay? To take one single measurement, in this case, you need two robots. because your sample is is taken when you have two robots in two positions that try to communicate with each other. And what you are covering is pairs of vertices. Okay, so you need two robots for performing the measure, and each measure will cover a pair of vertices. So in this case, you can use the same function, but the same covering function, but it has this special form. You need two robots for performing one measure, and you obtain a measure between 2 points. Okay, and okay. Of course, you can have several other definitions. So these are some examples of how the covering function can be defined. Usually, one important point is that the covering function is independent of the number of robots. So usually, in all the problems, you are defining the covering function with respect to a single robot or to two robots. Okay. And if you have multiple robots, each robot will have the same covering, let's say capabilities. And usually in problems, there is also a covering cost. So when you perform a covering action, this does not come for free, but you have to pay some cost in terms of time or in terms of, or in terms of energy. So the typical case is that when you have a range sensor, like a laser rangefinder, the time it takes for making a measurement is just 0, okay? It is almost instantaneous. There are, for example, some gas sensors that are able to detect gas concentrations that will take also some minutes for making one single measurement, okay? So, and in this case, you would like to take it into account for your problem. So then, in a coverage problem, what is your goal? So your goal is to cover, in general, all the environment. But if you would be more specific, your goal is to cover just a subset of your environment. So if you would like just to cover some relevant locations, then your target set, that is called M here, will be a subset of the vertices. So if you have a vacuum cleaning or low moaning problem, or a perception-based coverage, you would like to cover all the environment, so your target set M will be equal to V. And in the case of joint measurements for building communication maps that I have just mentioned, then you would like to cover a subset of the pairs of the vertices. So the goal is to cover M. And how is a solution represented? A solution is represented as a sequence of assignments that are S0, S1, up to Sm. And each assignment is basically a vector of assignment of one robot to one configuration. So we are just saying that at the beginning, all the robots are in their initial configurations. Then in S1, we reassign some robots to some other configurations. So we move some robots to some other places. And we don't need to move all the robots, okay, just some of them. And until we reach the number of measurements that is needed, that is the cardinality of the target set, okay? And the constraint on these sequences that when the robots are assigned to all these configurations in sequence, then the target set is fully covered by their covering actions. We can also embed in the solution the fact that the robots should not collide with each other, and this is basically done by imposing some constraint from moving from S0 to S1 and from S1 to S2. So not two robots can be in the same vertex, or they cannot swap vertices, okay? One robot is here and one robot is here. In one step, they cannot do like this because they are traversing the same edge at the same time, okay? And there are also no train, and there are also some other constraints that you can add. And okay, and as I said, we have these two objective functions: the total cost. In this case, the cost can be the sum of the movement costs and of the perception costs and the make span, and the optimal solution is, of course, those that optimizes the objective function that we have chosen. So this is the big picture of the multi-robot coverage problem, okay? And in this case, the path of the robots are basically embedded in this solution here. And as I said, in this case, almost all the algorithms, not all, but several of the algorithms are offline. So this means that you know the environment and you plan offline where the robot should go for covering it. Let me just show you some example of this. This is from 2005, and it is a very simple example, but just to give you the idea of some of the algorithms that are used in this case. In this case, they are using this spanning tree. Do you know what is a spanning tree? Okay, for those of you who don't know, I have put a definition here. Okay, a spanning tree is given a graph. A spanning tree is a tree, of course, that covers all the vertices of the graph with the minimum number of edges. So in this case, you have this graph here with this grid here, okay, and the spanning tree is composed only of the blue edges, okay? As you see, it is a tree. If you pick up, for example, this vertex here, so you have a tree, okay, and it has the minimum number of edges. So it is not difficult to understand this because if you remove one vertex, one edge, you disconnect the tree, okay? Okay, this is the idea of spanning tree. And this is something that comes from graph theory, okay? In this work and in several other works, okay, not only in this one, the idea is to use spanning trees in a multi-robot context. So the idea is the following. So we have a covering tool that is a square of size D, okay? And we have a grid environment in which each cell, the small cells here, okay, are of size D. So the edge of these cells is D. So is D times D, okay? And these cells are grouped in groups of 4, and then they are grouped in 4, like this is a supercell, okay? And the center of this supercell is considered as a vertex of a graph. So we have a supercell here, a supercell here, another one here, and so on. Okay, then the idea is to build a spanning tree over these vertices, which is basically the red one here, okay? And then the idea is to distribute a copy of the spanning tree to all the robots that start from different initial position in the environment. So the robots here are the blue dots here. And then each robot starts following the spanning tree in a counterclockwise direction. So this robot starts from here and goes like there, okay? Until Okay, it continues until it finds the starting position of the next robot. And then the next robot will start and so on. Okay? So this is very stupid, okay? It's not really smart, this kind of approach. But it has a very, very, very nice property that is robust. So this means that you can end up with the full coverage of the environment even if m-1 robots fail. You just need a single robot. Okay, so if n-1, in this example, if 2 robots fails, this one can continue to follow this tree and then come back to its initial position, and you have covered all the environment. So it is not optimal, because the main problem here is that the distribution of load of work over the robots will depend on their starting positions. Okay, if all the robots start from the same point, they do not divide their work between each other. They just follow. Okay, all follow the same path. Okay, this was 2005, okay. There have been some improvements on this. We will not discuss them, okay, but just to show you that this idea is one of the ideas that has been used for robot coverage. And the improvements try to work towards a better balance of the path, of the length of the path of the robots. Okay, so this is another example, 2008, okay, and in which we have in this case, I mention it because it is a situation in which we assume that the environment is unknown. So we have to cover an environment, but we cannot plan offline because the environment is assumed to be unknown. So we must resort to an online approach, to an online algorithm. And basically, this algorithm works in 2 steps. Okay, I'm just giving you the main idea. The first step is to find the cells. So basically, the idea is that you select some sweep direction, which is this one in this case, okay, and then you find a cell here. When you find, like, you are moving a line like this, okay, and when you find the critical point here, you can have these 2 cells, top cell and bottom cell. And then here is a critical point, and then the 2 cells are just merging together. I will skip several details, okay? I am not interested in all the details, but in just the general idea. Then, when you have a cell, how can you cover it? So the cell is something that you don't know from the beginning. So the idea is that you have 2 robots that are called Explorer, that are following the up and the bottom boundary of this cell. And then you have a number of robots that are called coverers that are going up and down like this. And this is the idea with which you cover a single cell. Okay, like you are moving in this direction using this pattern here. There are some tricky parts that are, for example, so in this case you have one group of robots here, one group of robots here, and they just merge here for covering this cell here. But what happens if the robot should split? Okay, and there are also mechanisms for splitting robots. In this case, half of robot will go up and half of robot will go down this obstacle here. Okay, and in this case, the environment is covered. Okay, this is the idea of this algorithm. It was bootstropedon. The bootstropedon means this kind of movement. Like when you are, it is also called low mower pattern. Okay, you are go up and down, up and down, up and down, and you are covering like this. Okay, of course this is not optimal because because it is online, and so okay. So there are several other approaches for solving the coverage problem. Just mention some of them here. One typical approach is to, when you have a single robot, the coverage problem is typically a TSP problem, a traveling salesperson problem. And the idea is to move from one agent, TSP, to MTSP, in which you have M robots. So this is something that has been shown also yesterday, okay, when illustrating the ROS framework for your experiments. So just to give you the idea and the formal definition. So in a single agent TSP, I think that everybody knows it. You have a complete graph means that you have edges between each pair of vertices, okay? A complete graph that is weighted, so you have a weight for each vertex. And the TSP asks for the shortest tour that visit each vertex. So this is a typical example of a TSP. It is, of course, well-known NPR problem, okay? And when you have multiple agents, you have MTSP, that is multiple traveling salesperson problem. And in this case, you have the same graph that is complete and weighted, but we usually have a depot, which is the starting point for the robots, okay? So we usually assume that all the robots start from the same point. There are also in this case several variants in which the robots can start from different positions and so on. But this is the basic formulation. Okay, and the goal is to find a set of M tours, one tour for each robot, such that the total cost of these tours, that can be either, also in this case, can be the sum of the costs or the make span, is minimized. So we have this example here. So we would like to cover all the vertices of this graph here, but with 3 tours, one for each robot, the green one, the red one, and the blue one, okay? And all the tours, in this case, of the robots are constrained to start and end at the depot, okay? Also, in this case, there are several variants. And it is not surprising, okay, that these kind of problems have been used for solving the multi-robot, the coverage problem. Another common approach that is used a lot in practical applications is the following. So you have to cover a number of vertices, okay? And you have M robots, okay? So the approach is a two-step approach. First, take the vertices and cluster them in M groups. One group of vertices for each robot. Then you assign a robot to each cluster, and then each robot will plan independently its own TSP over the vertices that have been assigned to him. Okay, so the two-step approach is I divide the vertices in subsets, one subset of vertices for each robot, and then I will use a single robot approach for each robot. And there are other approaches that are based on neural networks or that are bio-inspired and so on. There are a lot of variants of this basic problem that are based, you can add some communication constraints, or you can add the presence of a base station. So everything you discover should be communicated back to a base station. I will show you an example in a second. And also some other approaches will assume the presence of a cable that constrains the movement of a robot and so on. In practice, what happens is that if you look at the literature, there are a lot of solutions that are rather ad hoc, so they are very specific for single applications, so they work maybe in that specific application, but they completely lack theoretical guarantees. Okay, so there are several techniques that works maybe, but they have no solid theoretical base of theory. Okay. Let me just show this one. This is very, very recent work. It's a completely theoretical work. This EMAS this year. Okay. In this case, we have a graph. Okay, that should be covered, but we have two constraints. One is that it is not possible to communicate between each pair of vertices. So if you can see here, a continuous line is the movement, possible movement between the vertices, while the dotted lines are the possible communications between the vertices. So the first constraint is that, for example, in this case, it is not possible for a robot here to communicate with a robot here directly. Okay, and the second constraint is that when you cover this environment, you have to keep connection with the red vertex, which is the base station. Okay, so one possible execution is something like this. So you have, in this case, 3 UAVs. So one goes here, and this is covered. Okay, then also, sorry, here, and then this is covered. Then the robots are like this. Sorry for this. And then like this, and then like this. And as you see, these robots can always communicate with the red vertex. So from here, this can communicate with this one, and this can communicate with this one, and this can communicate with the base station. Okay, so they move with this constraint here. So they should always be in communication. This paper is not providing algorithms for solving this problem, but it is characterizing the difficulty of this problem. And it turns out that if you consider a situation in which if a robot can move from a vertex U to a vertex V, then two robots in U and V can communicate with each other, okay? So if you can move between two vertices, then you can also communicate between these two vertices, which is quite a reasonable assumption, okay? You can also communicate between other vertices, okay? But for sure, you can communicate between vertices from which you can move, and they show that this problem is p-space complete. So p-space is a class of complexity that is considered to include NP. So it is a really, really hard problem. Okay, p-space stays for the polynomial space, and it means that these problems can be solved by a Turing machine with a polynomial space memory, okay, in the size of the input, okay. Okay, and actually it is a class of very difficult problem. The paper has also several other results, but this is something that I would like to show, because if you add constraints over the communication, okay, then your problem can become really, really difficult. Okay. Okay. Now, as I have anticipated, this is one of our paper, this Emma's last year. In this case, we have to take measurements between pairs of location. So let's look at this example here. So I have this very stupid graph, okay? I have two robots, R1 and R2, and I am required to take these two measurements. I have to take a measurement between D and U, so I need one robot in D and one robot in U for making one measurement, and then I need to take a measurement between D and V. So one robot in D and one robot in V for making the second measurement. Okay? I must take these two measurements with two robots. Okay? So how can I minimize the sum of the distances? So the sum of distances is minimized in this way. So let's say that the robot 1 is fixed in D, robot 2 moves here, the first measurement is taken, then robot 2 moves here, the second measurement is taken, and then robot 2 comes back to the depot. Okay, so in this case the cost is 2 plus 3 plus 2, which is 7. Okay? Okay, it is very simple. Okay, so what if I would like to minimize not the sum of the distances, but I would like to minimize the maximum time, so the make span? Should I use the same approach or can I do better? Haha. Oh, this problem happens not only, so every time you need to make, let's say, it is also called mutual measurements. So you have just to, for example, there are some approaches that will localize two robots, okay, just making a measurement between them. Okay, and okay, these kind of problems are these, and if you would like to, are similar to this one. And if you would like to minimize the maximum time, you have to come up with a different plan. So if you would like to minimize the maximum time, your best plan is like this. Robot 1 stays here, and robot 2 goes here. Okay, so it will require 2. Okay. Then robot 2 comes back here, and robot 1 goes here. It will require 2. At the end, robot 1 will come back to here, so the total cost is 6 in this case, in terms of time. Why? Because moving from this configuration to this one, robot 1 moves from D to V, and at the same time, robot 2 moves from U to D. So you can do it at the same time. Okay. Okay, so in general, how can this problem be solved? Okay, this is a very simple algorithm that has some nice properties. So the simple algorithm is like this, is a greedy one. So if you have measurements to take, if you still have measurements to take, then just select the best possible measurement that you can take, and the best possible one is the one with the minimum cost. So the measurement which will add you the minimum cost to your objective function. Okay, and this is greedy. This is of course not optimal, but it has a polynomial complexity, which is very good, okay, and we have been also able to find some approximation factors. So we can be sure that we cannot be more far than this from the optimal solution. Okay, I will not go in the details here. Okay, but it was just to show you that the coverage problem can have some very strange formulations. So they are not really intuitive like covering an environment like a vacuum cleaner. Okay. Okay, yeah, we have some time for introducing the second canonical task that is exploration. What is multi-robot exploration? So from an intuitive point of view, is an online task that is performed to discover some features of an initially unknown environment. So typically, the features of the environment that you would like to discover is the presence of free space and of obstacles. But it is used but not only this, we will see later. It is used in a number of different applications. It is used for map building, for search and rescue, for gas detection, and so on. And a general formulation of the multi-robot exploration problem is like this. So you are given a space here, okay, that is initially unknown to the robot, or at least some aspects of this environment are initially unknown to the robot. Then you have mobile robots that are equipped, in this case, with some sensing tools, so tools that are able to sense something. And then the multi-robot exploration problem asks to find paths, one for each robot, such that when the robot will follow them, then the space E or its unknown aspects are known. And this is, as we have already discussed several times, it is a typical online problem. And we have two main variants of this problem. What I have called the frontier-based exploration and the information-based exploration. So in the first case, what it is unknown is the geometry of the physical space. In the second case, what is unknown is something in the information space. So for example, in the frontier-based exploration, you don't know how the environment is structured, and you have to discover it. In the information-based exploration, you may know the environment, okay, the structure of the environment, but you don't know, for example, the temperature. And you have to discover the temperature or the gas concentration in the environment. Something in not in the physical structure of the environment, but in the, let's say, what is called information space. Okay, a solution being an online problem is a strategy or a policy, okay, it's called also sometimes, that given the knowledge that you have acquired so far about the environment, that we call a map, okay, says which robot should move. So in the very basic formulation, so this policy, given what you know up to time t about the environment, says that robot 1 should go to vertex v1, robot 2 to vertex v2, and so on. So vertex is a configuration of the, is in general a configuration. And the sequence of these decisions, of these assignments, will achieve the global goal of the exploration, which is that your representation of the environment, your map, will contain all the knowledge that you need about the environment. And you are usually looking for efficient solutions in terms of time, so to minimize the time, to minimize the traveled distance by the robot, the distance traveled by the robot, to minimize the energy consumption, and so on. Also, in this case, it is quite possible that a policy will prescribe that one robot stays still from time t to time t plus 1, if it is needed for some reason. So the basic setting in which these robots operate is like this. They perceive the environment. They integrate this perceived data into some representation, into a map. So they decide where to go next and who goes where. And then they move to the destination locations. And then they repeat this cycle for the next step. So the most important part from a decision-making point of view is to decide where to go next and who goes there. So it's step 3. And this basically amounts to two different decisions that are called usually exploration strategy and co-ordination method. So exploration strategy means identifying which are the interesting points to reach. And co-ordination method means deciding which robot should go where, which robot should reach which interesting point. So let me see how this let me show how this basic framework applies to frontier-based exploration. So this is a single robot exploration, but just to give you the idea. So the goal here is to discover and map the free space and the obstacles in an initially unknown environment. What are the exploration strategies? In this case, the exploration strategies means finding what are the interesting points that the robot should reach. And starting from 1998, the work by Yamauchi, the basic idea is to move the robots toward the frontiers. And the frontiers are the boundaries between what you know and what you don't know. Okay, so in this example here, it's not really clear, but this area here is what the robot knows, and these dashed lines are the frontiers, so are the boundaries between the known part and the unknown part. And the exploration strategy just order or rank these frontiers here. So for some reason they say that, okay, P2 is more interesting than P3, which is more interesting than P1. Okay? And why this? You can use different criteria for coming up with such ranking. And the typical approach is to use a utility function. So you have some frontiers, okay, in your environment, and you evaluate them using an utility function, which is a function that combines a number of different criteria. I list some of them here, the most used, but there are several proposals with several other criteria. So a typical criterion is the amount of free area that you expect to see beyond this frontier. If you go back, if you go back here, in this case, this frontier seems to be more interesting because even if we don't know what is on this side, but it is more interesting because it is very long. So long frontiers are usually more interesting, okay? Because you expect to see more beyond these frontiers, okay? Then the other typical criterion is the distance between the position of the robot, R, and the frontier. This can be calculated like the Euclidean distance or with some path planning approach. The battery of the level of the battery of the robot and the probability of communicating with some base station and so on. All these criteria are combined in different ways. So also here there are hundreds of approaches. The first one by Yamauchi just said that, okay, select the closest frontier. So the only criterion that you use to select frontier is the closest one. Then, okay, this is González Baños and De La Tom, 2002. okay, they say, okay, we can combine the expected area that we can see beyond this frontier here and the distance to reach the frontier in this form here. So it is an exponential function. Okay, this lambda is a weight. Okay, and another approach is by Arnaud Visser and Slamé, 2008, and they say, okay, no, not the exponential function, but this fraction. So this is the amount of area that I expect to see from the frontier. This is the probability of communicating with the base station. And down here, we have the distance that we have to travel to reach the frontier to the power of the battery that is left for the robot. Of course, usually all these quantities are normalized, okay? Just to have the same scale, but okay. It is not important. So all these functions, there are a lot of them, are ad hoc functions. So this means that they are, there is no principle for finding these functions. So they work, okay, it is fine, but why here we have an exponential here, why we have this fraction here and not minus or something like that, it is not theoretically grounded, okay? In the past, in the very past actually, we have proposed some more principled way to aggregate these criteria in an utility function, but I will skip them because I would like to say another thing before stopping for the coffee break, so I will skip this one, okay? And I will go to the coordination method. So with the exploration strategies, we have decided that P2 is more interesting than P3, that it's more interesting than P1. Now we have this problem. We have two robots, R1 and R2. Which robot should go where? So one typical thing is that, okay, P2 and P3 are the two most interesting points, okay? So let's send one robot to here and one robot to here, okay? And this is exactly the idea of the coordination method. This is an instance of the solving this problem is an instance of the task allocation problem in which we have some robots, we have some tasks which are the frontiers to reach, and then we have to combine these two elements. The typical approach is market-based, so this means that typically there is some central entity, but it can also be implemented in a distributed manner. There is a central entity that requests bids from the robots and assign the tasks according to the received bids, so to the best bidding robots. So the idea, for example, is embedded in this algorithm by Visser and Slamé, and they say, okay, for each robot and each new and each frontier, we compute the utility of the frontier for the robot using one of the previous approaches. Okay, then we find the maximum, the pair frontiers P star and robot R star that maximizes this function here. And then we refine this number here. This is quite technical. So the first computation of the utility has been done using the Euclidean distance between the robot and the frontier. This is because it is very quick, okay? Then for the best one, we refine this and we compute the path planar distance. So this requires a lot of time, usually, but sometimes it happens that a robot and the frontier, which are very close from a line of sight point of view, they are very far from a path planar point of view, because for reaching that point I can make a very long path. Okay, and if this is still the best allocation, then I will allocate the frontier to the robot, and then I will eliminate the frontier and the robot from the next allocation. And then I will use this greedy approach for allocating robots to frontier. This is an instance of the market-based approach because it is like that each robot is submitting its bid for each frontier. And its bid is the utility of the robot for the frontier. What is the interplay between exploration strategies and coordination methods? So how much effort you should spend on designing exploration strategies and on designing coordination method. We have done in the past some experiments on this. I will skip the details and just come to the main result. So we have found out that in structured environment, if you use good coordination strategies, is better than spending too much time in coordination. And in open environment or less structured environment, then the coordination will become more and more important. So this is something that can be explained from an intuitive point of view in this way. If you have a very constrained environment like this, the coordination between the robots is in some sense enforced by the structure of the environment. Okay, so for example, if you are in this corridor, okay, you will have one frontier on this side and one frontier on this side, and then if you have two robots, you will assign one to one frontier and the other one to the other frontier, so they will be spread in the environment according to the structure of the environment. And if you have some large open spaces, then you need some more coordination to avoid, for example, that two robots go to the same position in the environment. Okay, so I think that it's time for the coffee break, so I can stop here, and then we will continue in the two parts in this afternoon.
Thank you,
Okay.
Francesco.
Okay.
We have still a couple of minutes for questions, so if you have
yeah.
some.
Thank you for the presentation.
Oh, sorry.
Thank you for the presentation. So how do these algorithms scale up when we go from 2D to 3D?
Yeah. Okay. From the point of view of the algorithm, it is a problem. This is because all these problems are hard problems. Okay. So if you represent your environment as a graph, if you have a 3D environment, so you can still represent it as a graph, but the graph is huger, okay, is more large. And in this case, the optimal algorithms that are already inefficient in 2D are still more inefficient in 3D. As I said, there are several practical algorithms that work, like, for example, for edge coverage, one typical approach that works well is to cluster the points and then assign them to the robot. And from the point of view of the distributing the robot using this approximated algorithm works very well, okay? Also in 3D. What is the difficult part is, for example, the path planning part. Okay, so once I said, so you have to follow these, and then you have 6 degrees of freedom or something like that. It's more complex to actually have a trajectory planning for following the path. So from the point of view of the algorithm, the optimal algorithms are already inefficient in 2D, but the approximated algorithm works well.
for the algorithm you said about the spanning tree, the first one. Yeah, I didn't understand why that's a multi-agent situation when you have like, you're not minimizing time or like distance. Like, I don't understand why you have more than one agent there. Because one agent can just do the whole thing, right?
Yeah, okay. But if you have multiple agents, okay, you can split the work over the agents.
Like, you mean in terms of like battery time?
Sorry?
Because the next agent has to wait for that agent to reach him, right? And then that agent will start, right?
Yeah.
So you're not minimizing time.
No, you can save time because okay, let me just. So the idea is that, okay, yeah, you can save time because this agent here has only to cover this path up to here, okay?
Yeah, what my question is that this thing can be done by one robot, right? Like, you don't need the other
Yeah,
agent.
okay.
Yeah, so this is like...
No, okay. Okay. The sum of the distances is still the same.
Yeah, and even the time, right? And even the time, if it was only one.
If you look at the sum of the distances, you don't have any advantage in using an agent and in using one single agent. But if you are looking at the make span, okay, at the time that you need to cover the environment, if all these agents are moving at the same time, okay, if all the agents are moving at the same time, you can save some time.
Yeah, so it's not part of the algorithm that the agent has to wait for the... Like, you don't just pick one and then it goes to the next one and then you go? Like, you can move them all in the same time?
No, they can move also at the same time. They can move also at the same time, yeah.
Just for this one, then we need one additional algorithm that will distribute initial position of the agents. Because also, like, if we look at some real applications, we are starting agents from the same point. And then we have additional time that agents reach the point.
The idea is that at least for these by Noah, Agmon, and others, the idea is that actually one thing that I have not said is that you can, given a graph, you can build several spanning trees. Actually, it is a large number of possible spanning trees that you can build. So the idea of this improvement is that select one smart spanning tree such that given the initial positions of the agents, they can be split over different branches of the spanning tree. So even if they start from the same position, and my spanning tree is smart, okay, if I have 3 agents, I can have 3 branches starting at the very beginning, which is not this case, okay? Which is not this case.
Hi. I mean, this may vary depending the technique, but how do these, at least these coverage techniques, scale with with increase of the number of robots? I mean, roughly speaking. Let's say,
okay. The answer, of course, it depends on the techniques. Okay, everything. Yeah. But in general, is the same answer to the previous question. So if you are looking at the optimal the solution, they do not scale well, okay? Because usually we are dealing with NP-hard problems, okay? And if you are looking at approximate solutions, then they can scale really, really well.
Yeah, but when you say that, when you are talking about the optimal solution, they don't scale well, we are talking about 10 robots, or are we talking about 100 robots? I mean, of course, this depends also in the environment and the model.
It depends on the algorithm. It depends on the several things. It depends. So if you point out a specific algorithm, I can give you a precise answer. Sorry, but
thank you. Yeah, I understand. Yeah.
Yeah,
It makes sense.
Yeah. So for example, just one well-known result. So if you use multiple TSP, there are very good approximation results. Okay, so you can solve a single TSP, okay, and then split it in a number of parts that is the number of robots, okay, and you can have some bound over the worsening of the quality of your solution, and this is really very effective in several cases. But this is just one example on one specific technique. Okay.
Thank you.
Yeah.
Yeah. So if this is everything, thank you. I have also the small present for you because your next presentation will be splitted. So I want to thank you with all the audience with us. So thank you very much for coming.
Thank you very much.
Thank you very much.
Thank you.
And yeah, let's go to enjoy coffee break. And please come in 15 minutes, really. Thank you.
Thank you.